Good morning to all of you. We will continue with our discussion on electrostatics. In the last class, I introduced the concept of a dipole, and we were calculating the electric field of a dipole at certain positions. And so, let me recall, a dipole consists of, so this is an electric dipole. It consists of a negative charge minus q and a plus q separated by a distance which I am calling 2a. So, this is a dipole, two equal charges, one minus q, one plus q, separated by a certain distance 2a. Note that the total charge of this system is 0, but as we saw last time, in spite of this fact, it still produces an electric field, because the two charges plus and minus are displaced with respect to each other. So, in the last class, we calculated the electric field at a certain distance x from the center of the dipoles, and we showed that E is equal to P by 2 pi epsilon 0 x cube into I cap. So, this is the x axis. Sorry, this is no I cap here. So, P was defined as q times 2a times I. So, the charge multiplied by the separation between the charges, and it is a direction from minus charge to the plus charge. So, that is the definition for this quantity P, which is called the dipole moment. Dipole moment is a characteristic of the dipole itself. It depends on the charges and it depends on the separation between the two charges. So, q times 2a is the magnitude of the dipole moment, and the direction of the dipole moment is along the line joining minus charge to the plus charge. So, one thing to notice here is that the electric field decreases as 1 by cube of the distance from the center of the dipole to this point on the axis. Compare this with electric field of a point charge. The electric field of a point charge reduces as 1 by square of distance. This is reducing as 1 by cube of distance. So, that is along the axis. We have got a simplified expression, and this expression is valid for large separation. That means, x must be much greater than 2a. We can now calculate also through a simple calculation the electric field on the equatorial plane. So, this is plus q. So, minus q here, plus q here. So, this is the x axis and this is the y axis, and so I take a point here, point P, at which I want to calculate the electric field. So, remember, this particular charge will produce an electric field in this direction, this particular charge will produce an electric field in this direction. So, the electric field is directed towards the negative charge because of the negative charge, and away from the positive charge for a positive charge, and this is on the equatorial plane here. So, let me assume this distance is y, and so let me draw a horizontal line here, and this angle I call theta, which is the same as this angle, and this distance is a. So, what is the electric field produced by the plus charge? So, let me write E plus q 1 by 4 pi epsilon 0 q by distance square. So, let me call this r. So, r square, and it is along this direction. So, this direction has two components, one along the x axis and one along the y axis. So, let me draw this here. So, here is my y axis here, the electric field goes like this because of the positive charge, and this angle I am calling theta, and this is my x axis. So, x component is minus cos theta I cap, and y component is sin theta. So, sin theta j cap. The electric field, because of this plus charge at this point, has two components along the x axis and along the y axis, which are given by minus cos theta I cap plus sin theta j cap. Similarly, the electric field, because of the minus q charge, is 1 by 4 pi epsilon 0 q by r square. Again this distance is also r, because I am taking the point P on the equatorial plane, and then this now this angle is also theta. So, I will have again minus cos theta I cap, and then I will have now y component is negative. So, minus sin theta j cap. So, the electric field of the minus charge is along this direction, the electric field of the plus charge is along this direction. So, I can calculate the total electric field at the point P, which is given by E is equal to E because of plus q plus E because of minus q, which is equal to 1 by 4 pi epsilon 0 q by r square. So, I get minus 2 cos theta I cap. The j cap component cancels off, and I am left with an I cap component only, which is minus 2 cos theta. Now, I want to express theta in terms of the distances. So, if you go back to this figure and see, this is theta. So, cos theta is equal to a by r. So, I have essentially E is equal to 1 by 4 pi epsilon 0 q by r square minus 2 cos theta is a by r into I cap. So, this is equal to q by 4 pi epsilon 0. So, 2 a with a minus sign here I and r cube, and this is nothing but minus p by 4 pi epsilon 0 r cube. Now, r is the distance from the positive charge to the point where I am calculating, or is also the distance from the minus charge. So, I can express r in terms of a and y. So, I get the following expression: r square is equal to a square plus y square. So, E total becomes minus p by 4 pi epsilon 0 a square plus y square raised to the power 3 by 2. It is r cube. So, I have a square plus y square raised to the power 3 by 2. So, if y is much greater than a, then E becomes equal to minus p by 4 pi epsilon 0 into y cube. So, you see here again that the electric field produced by the dipole on the equatorial plane is also varying as 1 by y cube, where y is the distance of this point from the center of the dipole, just like for the x dependence where it was 1 by x cube, here it is 1 by y cube, and the direction of the electric field is along the minus p direction. This is also obvious from here, because if I plot the figure here now, minus q plus q. So, on the equatorial plane somewhere here, this plus charge produces a field like this, the minus charge produces a field like this. So, the net field actually is in this direction. The y components cancel, x components add, and you know that p vector is like this, from minus to plus, and the electric field is like this in this direction. So, that is the minus p cap direction, minus p vector direction. So, that is the electric field along the equatorial plane, and electric field along the axis varied as 1 by x cube. In principle, I can calculate the electric field at any other point simply by writing the total electric field as a sum of the electric field because of plus q and minus q, and we can always calculate, but here in this course you will just calculate along these two directions, which where we get simplified expressions. So, I must mention here again that these expressions we have got are for distances much larger than the size of the dipole. Now, it is possible to define what is called as a point dipole by letting the separation between the two charges become smaller and smaller, that is a tends to 0, a can be tending to 0, and the same time q tends to infinity. So, that q times 2a is a constant, becomes a constant p, and that is called a point dipole. The separation between the two charges is very small, smaller and smaller, at the same time the charge is increasing, so that you have a very small dipole, and that is like a point dipole. So, Why are we discussing dipoles? I will show you some physical significance of these dipoles. So, let me show you some slides. Okay. So, here is a slide which shows where the dipoles appear in an actual system. On the left of the figure, I have shown a neutral atom consisting of a positively charged nucleus, which is shown as the dark sphere, and surrounded by a cloud of electrons. The electrons form a cloud around the nucleus, and usually the center of the positive charge and the center of the negative charge coincide at the center of the entire system. And so, the dipole moment of this is 0, there is no dipole, the total charge is also 0, and this is typical atom when in the absence of any external electric field. Now, what happens when I apply an external electric field? Suppose I put this atom inside a capacitor which contains 2 plates where there is a very strong electric field, then the electric field, suppose as shown in the second figure, the electric field is pointing upward. So, what happens is the electric field pointing upward pulls the electron cloud downwards and shifts the position of the center of the negative charge with respect to positive charge. So, you have a small shift between the negative center and the positive center, forming a small dipole. So, the presence of the electric field converts the atom which had the centers of the positive and negative charges coinciding into a dipole, and this dipole then creates its own electric field. So, the electric field created by the dipole adds to the electric field that you have supplied from outside to get the total electric field. So, we will come to this picture again a little later when we discuss dielectrics, because dielectrics and insulators consist of atoms, and when they are put in electric fields, then you displace the negative and positive centers of each of the atoms in the dielectric, resulting in a certain effect which we will discuss later. As a very interesting molecule which has a very strong dipole moment, this is water molecule. Water is H2O, it consists of 2 hydrogen atoms and 1 oxygen atom, and the bonds are formed such that, as drawn in the figure, there is an angle of about 105 degrees between the HO axis of the 2 HO axes. So, what happens in this bond formation is electrons actually are more crowded towards the oxygen atom, leaving the hydrogen atom as positive, with the result that the center of the negative charge and the center of the positive charge of the whole system is separated, resulting in a dipole moment. So, water is a molecule which has a dipole moment even in the absence of any external electric field. Like in the earlier example, I showed an atom in which dipole gets generated when you apply an electric field. Here the dipoles are already formed in water. The water has a finite dipole moment, and the dipole moment of water is given approximately here as 6.1 10 to the minus 30 coulomb meter. Now, this particular dipole moment of water molecule has extremely profound consequences. Because of the strong dipole moment, it is an excellent solvent for ionic substances like salt. If water molecule was not a dipole, it would have been a poor solvent, and what would have happened is all chemical and biochemical reactions would have been impossible. So, in fact, we can say that our existence as living beings depends on these electric dipoles of water molecule. And you may ask, why do not the oxygen atoms and the hydrogen atoms stay along a straight line? That is explained by the quantum mechanics, principle of quantum mechanics, which explains why the molecule has this particular shape. So, this is a very important molecule in living systems, and it has a permanent dipole. It is called a polar molecule because it shows a dipole moment even in the absence of electric fields. Okay, so, dipoles are very important, and this is the reason why we started to look at electric fields of a dipole. Now, let us also see what will happen if I keep this dipole in an external electric field. So, let me assume that I have a dipole which I mark here as minus q and plus q. This is the axis of the dipole. Let me assume that this dipole now, on this dipole I apply an external electric field. Please remember, this is the external electric field, not the electric field of the dipole, but the externally applied electric field, I apply an electric field from outside, uniform electric field. So, E is the same everywhere, it is pointing upwards in the figure. Now, what is going to happen? This electric field is going to have a force on the minus q charge in this direction, force will be minus q e, and on this charge it will have a force in this direction q e, two forces on the 2 points of the dipole, equal magnitude. So, net force becomes 0, plus q e on this charge, minus q e on this charge, total force on the charge on the dipole system becomes 0. But because the two forces are acting at two different points, this will induce a torque in the system, and we can actually calculate the amount of torque that this force will generate. So, I can calculate the torque by noting this distance. So, if this angle is theta, so this is the electric field actually. So, theta is the angle between the dipole moment and the electric field direction which is being applied from outside. So, this distance I have called it 2a. So, this distance is 2a sin theta, 2a cos theta. Sorry, this is not theta, sorry. So, this is 2a sin theta, this angle is theta, this angle is theta. So, these are two opposite angles here, theta and theta. So, this is 2a sin theta. So, the net torque, let me calculate, is the force q e multiplied by 2a sin theta, the magnitude of the torque, net torque magnitude. Now, q into 2a is the dipole moment. So, p e sin into sin theta. Now, if you look at the figure again here, so you had the minus q plus q, this is p, this is e, and this is theta. So, what is this product? P cross e magnitude, this is p e sin theta. P cross e is p times e into sin theta, the sine of the angle between these two. So, the magnitude of the torque is nothing but p e sin theta. And what is the torque trying to do? This force is trying to pull it, this force is trying to push it. So, this torque is trying to align the dipole along the electric field. So, this charge will, suppose this point is fixed, around this point this two charges will move like this and align itself until theta becomes 0. When theta becomes 0, the net torque becomes 0. So, this dipole is tending to rotate in this direction, and this is the direction. If I look at this vector in the upward direction, that is the direction of right handed screw. So, I can define the torque as a vector tau is equal to p cross e. So, the net torque on the dipole is the cross product of the dipole moment and the electric field. The magnitude of this torque is p e sin theta, and the direction is shown by this vector, which is p cross e, direction of p cross e vector. So, whenever you put a dipole in an electric field, external uniform electric field, if you put like this, the positive charge tends to align like this and the negative charge, and then when theta becomes finally 0, the torque becomes 0 and the dipole gets aligned like this. Now, I would leave a problem to you. Please think of any other situation, any other position when the torque can be 0 again on the dipole. Please try to find out if there is any other position. But and so, in a uniform electric field, there is no net force on the dipole, but there is a net torque on the dipole. So, if you put an electric field, if you put a dipole with an inside a uniform electric field, the electric field will tend to align the dipoles such that P and D become parallel to each other. Now, what will happen if the electric field is non-uniform? So, non-uniform electric field. That means, electric field depends on position. Now, I do not want to discuss a general situation, but one particular situation where I will assume that there is a minus q here and there is a plus q here, and this is aligned already. So, so this is the electric field. So, let me assume that electric field direction is this, and let me assume that electric field is not uniform now. So, the electric field may be increasing with x, if I call this x direction here, or maybe decreasing with it. So, electric field is different at different values of x. Now, what is going to happen? There will be a force here q E on this charge. Let me call E at minus q, and this is q times E at plus q. So, this force is okay. So, this force is along the x direction, this force is along the minus x direction. So, net force along x direction is equal to q times E at plus q minus E at minus q. So, this force is trying to push it, this force is trying to pull it. So, effectively the net force is the difference between these two. So, if E minus q is bigger than E plus q, that means if there is a decrease of electric field like this force will be negative, which means that the dipole will be pulled in the minus x direction. This is the force along the plus x direction. So, I have the dipole sitting here, there is a force trying to push this, there is a force trying to pull this. So, the net force on this will depend on this quantity. So, if my electric field is stronger on this side and gets weaker as I move up, electric field at this point is more than electric field at this point, the force on this is greater in this downward direction than the force on this. So, the resultant force will be in the downward direction. So, in a non-uniform electric field, what happens is the dipoles are pulled towards stronger electric fields, because the electric field is decreasing in this direction, the electric field here is larger than the electric field here, the charges are exactly the same. So, the downward force is more than the upward force. So, the net force on this dipole is to pull it towards the larger electric field, and it comes here. This is exactly the reason why in the first experiment which I showed you, charged glass rod was picking up paper. So, what happens is when you have a charged rod kept near a small object like a thin piece of paper, then it induces the positive charge on the glass rod induces a dipole in the material, and because the electric field is stronger near the glass rod than away from the glass rod, it pulls the dielectric towards the glass rod. So, we will discuss a little later more discussion on electric fields inside matter, but for now this non-uniform electric field actually results in a force on the dipole. If you have a uniform electric field, there is no net force, there is only a torque on the dipole. So, this will become important when we discuss more subjects, more discussion on dielectrics, etc. later. Now, before I move to further discussion on continuous charge systems, etc., I thought I will mention to you some very interesting facts which appear in nature. Okay, I want to show you some very interesting effects that take place in biological systems with electric fields. So, we as human beings have essentially 5 primary senses. We can see over a certain spectrum of radiation from 400 nanometers to about 800 nanometers of light. We can hear sound over a frequency from a few hertz to 20 kilohertz. We can smell, we can taste, and we can have a feeling of touch, a sense of touch. Now, nature produces many other signals. For example, there is radiation in the ultraviolet region, there is radiation in the infrared region, there are electric fields and magnetic fields, etc., which we do not seem to be sensing. But there are in nature many biological, many natural systems which use some of these for sensing. So, I will show you something here which is very interesting, that electrostatics is playing a very important role in nature. So, research has shown that flowers have a small negative charge on them, and when bees are flying, they are stroking their wings, and this through friction gives them a small positive charge. So, the bees have a small positive charge, the flowers have a slight negative charge. So, as the bee flies towards the flower, it senses this electric field, because the electric field actually affects its hair on its body, and that results in the bee sensing the electric field. So, when the bee lands on the flower, the pollens being negatively charged stick to the bee, and the bee carries the pollen, and as we know this helps the flower to pollinate. And not only that, when one bee has visited a flower, the electric field of the flower after the bee leaves is slightly different from before, and the bees which come afterwards are able to sense the change in the electric field and know that this particular flower has maybe less nectar because this has already been visited by some bee earlier. We all have seen many spider webs. The spider webs are covered by electrically conductive glue, and it seems that whenever you have a charged particle crossing nearby, it could be some charged particles like pollens or insects, and then these webs actually get attracted towards the insect and catch the insect. The webs also seem to distort the electric field of the earth over a small distance, which can be sensed by many insects such as bees. So, very interesting effects that take place in nature, and I am sure all of you have heard about the very strong electric fields some fishes use for their navigation or catching prey, and one of the most famous one of them is the electric eel. So, it actually produces different kinds of electric fields, low voltage pulses to sense the environment, extremely high voltages up to 600 volts to stun or kill the prey. And so, depending on the requirement, it either produces low voltage pulses for sensing or short sequence of pulses for hunting, and finally, a high voltage volley, a string of high voltage pulses for capturing or defending itself. There are other animals like elephant nose fish, which actually uses electric fields to navigate in murky waters. Sharks, which are extremely sensitive to electric fields, that they can detect voltage gradients of 1 billionth of a volt, and of course electric rays, which also generate voltages ranging from a few volts to 220 volts. So, these are actually effects that we find in biological systems which are able to use electrostatics for their applications. We as humans do not seem to possess real sensitivities towards these effects, these electric fields and magnetic fields. Okay, so, what we have discussed till now is how to calculate the total electric field produced by a distribution of point charges. We know the electric field produced by each point charge through Coulomb's law, and then we actually use the principle of superposition to calculate the total electric field if you are given a distribution of point charges. So, we add the electric field produced by each point charge at a point where we want to calculate, and add vectorially and get the total electric field. Now, there are many situations where we would like to look at what are called as continuous charge distributions. So, there are three types of charge distributions. One is called volume charge density. This is usually written as rho and has units of coulombs per meter cube. Then you have surface charge density, usually written as sigma coulombs per meter square, and then you have line charge density, usually written as lambda coulomb per meter. This is rho, sigma and lambda. So, these are the volume charge density is the charge per unit volume, surface charge density is charge per unit area, and line charge density is the charge per unit length. Now, these are three Greek letters. You will come across many of these Greek letters in your courses in physics, chemistry, mathematics, etc. So, it may be interesting for you to know that there are actually 24 Greek alphabets. So, these are alpha, beta, gamma, delta, epsilon, zeta, eta, theta, iota, kappa, lambda mu nu psi omicron pi rho sigma tau epsilon phi chi psi omega. There are 24 Greek alphabets, and you will find this use of these in many situations. We have already seen epsilon 0. We will now come across lambda, which is the charge per unit length. We will come across sigma, charge per unit area, and rho, which is the charge per unit volume, and you will see many other of these. Theta is an angle that we typically use, delta is used in differential calculus, etc., etc. So, we will come across many of these symbols. It is worthwhile for you to remember these symbols and be able to write them freely and nicely in your class notes. Okay, so, how do I define these various charge distributions? So, first is volume charge density. This is defined as charge per unit volume. So, let me take an example. I have a sphere in which a charge of capital Q, the sphere is of radius r, charge of capital Q is distributed uniformly throughout the volume of the sphere. It is like having uniform distribution of mass in a sphere. So, here is the charge is another characteristic of a particle. So, I have charge distributed uniformly. I take a small unit volume inside and I can define this is the charge per unit volume. And it has units of coulomb per meter cube. Now, we must remember the charge is actually quantized and they are charges distributed like particle charges. So, the volume that we need to take is large compared to the separation between these charges, but small compared to the size, macroscopic size of an object. And so, the charge it is like mass per unit volume that we define density, where you take a small volume, a small infinitesimal volume containing a large number of molecules, but that volume must be small compared to the macroscopic size. So, you take a small volume, say delta V, and calculate the charge in that volume delta V, and that charge comes out to be delta Q. So, you define rho as delta Q by delta V in the limit of delta V tending to 0. So, you have a charge per unit volume. So, we will later on calculate what is the electric field produced by such a distribution of charges after we discuss certain new concepts in electrostatics. So, that is how we define the volume charge density, which is charge per unit volume. Now, I come to surface charge density. Now, to explain surface charge density, let me take the following situation. Let me assume that I have a thin sheet of thickness d. It's a huge surface. So, let me take in this an area A. Let me assume that in this volume the charge density is rho. So, charge per unit volume in this small, it is a thin layer of material, it has charge distributed across the volume, and rho is this volume charge density inside this material. So, the charge contained in this volume which I have drawn here, which is equal to the volume of this material, which is the surface area multiplied by the thickness, this is the volume, into rho. This is the volume of the material and this is the volume charge density. So, that is the charge contained. Now, I write this like this, A times rho into d. Now, what I do is I let the thickness of this surface tend to 0, and at the same time increase rho to infinity, such that rho times d is a constant, and this is called sigma. So, in the limit of thickness d going to 0, I will just have a sheet having a certain charge. I am letting the thickness go to 0, simultaneously letting the charge density go to infinity, so that the product of charge density into thickness becomes a constant sigma, and so this becomes A times sigma. So, I will have sigma is equal to q by A, which is charge per unit area. Remember, q was the charge within this volume. As I let my thickness go to 0, the charge is in that area, and so I define the charge per unit area as sigma. And so, this is the charge which is supposed to be on one surface, all the charge sitting on the surface, and I have obtained this as a limiting process of a volume charge density. I can similarly define a line charge density by considering the following. So, I take a cylinder of cross sectional area A, and in this cylinder I take a length L, and let me assume again I have a volume charge density rho. So, the charge contained within this volume of cross sectional area A and length L. So, what is the volume of this? Volume is equal to A times L. This surface area multiplied by the length is the volume. So, and the charge density is rho. So, total charge q is equal to rho times A times L. So, I write this as rho times A into L. Now, what I do is I decrease the area of this cylinder towards 0, A tending to 0, rho tending to infinity. So, that rho times A becomes a constant which I call lambda. So, I am letting the thickness, the cylinder area cross section go to 0, simultaneously increasing the charge density. So, that this product remains a constant lambda, and then I get the charge contained in this length L is lambda times L, and so I get lambda is charge per unit length. So, this is called a line charge. It is a line, and line has no thickness. So, the line is just one line in which it has no thickness, and the charge I can define a charge. So, I take a unit length of this line, and I will find a charge is equal to lambda. So, what I have done is I have shown you that starting from volume charge density, I can define a surface charge density by having a certain thin surface, thin sheet, and allowing the thickness of the sheet to go to 0. At the same time, letting the charge density go to infinity, volume charge density go to infinity, with the result that I land up with a single sheet of charge, which is called surface charge density, which is called sigma. And then I showed you through a cylinder that I can make the area of the cross section of the cylinder go to 0, and the charge density rho to infinity, so that the product remains a constant lambda, and I get lambda as the charge per unit length. So, there are three kinds of primary charges, charge densities: line charge density, coulomb per meter; surface charge density, coulomb per meter square; and volume charge density, coulomb per meter cube. So, we will use these later on after we discuss some more of electrostatics. We will calculate what is the electric field produced by a line charge density, typical line charge density, surface charge density, and volume charge density. So, it will be interesting at that time to we will come back to these charge densities. I have just introduced them here. So, in principle it is possible, for example, if I am given a line charge like this. So, line charge density lambda, if I want to calculate the electric field at any point, what I would have to do is to take a small element here and calculate the electric field because of this element at this point, and add up all the elements on the line charge to get the total electric field here. So, I will later on I will use a very general principle which is which we will discuss after this preliminary discussion on charge densities, and I will show you how to calculate the electric field of this, and at that time we will come back to this method and we will compare the two methods, and I will show you that method is much more powerful than this method. Okay. So till now what we have seen is essentially calculation of electric fields. We have seen electric field lines, we have calculated the electric field due to dipole and so on. Now I want to introduce an alternative discussion of calculation of electric fields. The question is, given a charge distribution, I have been able to calculate electric field. Given the electric field, can I calculate the charge distribution? So this particular question was answered by a very famous scientist, Carl Friedrich Gauss, a German scientist who lived in the year 1777 to 1855. He is a great scientist who has contributed to many fields including mathematics, astronomy, optics, electricity and magnetism, statistics and surveying, geodesy. He is considered as one of the greatest mathematicians of all times. In fact, at the age of 18, Gauss discovered how to construct a 17-sided polygon using only a ruler and a compass. That was an amazing discovery at that time, and after that he has contributed significantly to the development of these many fields which I just now mentioned. So what we will do is, he introduced a very, very important law in electrostatics called Gauss's law, which relates electric fields and charges, charge distributions, and which will be very useful for us when we discuss electric fields produced by different kinds of charge distributions. Now before I discuss Gauss's law, we would need to introduce certain concepts in mathematics, which I will very briefly introduce here. Now we know that angles in a plane are measured in radians. So how do you measure an angle in radians? So what we do is, we take this point, draw a circle around this point of radius r. This cuts an arc length L on the circle. So we define the angle theta in radians as L by r. This distance divided by this distance is the angle in radians. So if you take a, there is no requirement on r. If you take a bigger circle of bigger radius, L will also correspondingly increase. So this angle will be independent of the radius you have chosen. So you take a certain, around this point you draw a circle of radius r, calculate the arc length subtended which is intersected by these lines, these chords, and you from there you can calculate what is the angle in radians. So if you take the entire circle, we know that the if you take a point and the entire circle, L becomes equal to 2 pi r, and the entire angle is 2 pi. So 2 pi radians. All of you know that 2 pi radians is the entire circle. This is pi by 2 radians, etc., etc. So this is a one of the very interesting definitions of angles here, and this is in a plane. Now I want to introduce an angle for not a plane, but in 3 dimensions. So we define what is called as a solid angle. So suppose I have a point here, I draw a sphere around this point, sphere of radius r, and if you draw a cone around this from this point onto the sphere, it intersects the sphere in a certain radius, in a certain area, say S. S is the area. So I have a sphere, and I draw a cone here. So that's a cone, and the cone comes out from the center and intercepts the sphere on an area. So, I will define this angle, this solid angle, as S by r square. The area intercepted by this cone on the sphere divided by the square of the distance. You see it is dimensionless here. So, you have S is area which has units which is dimensions of square of length, and that is square of length. So, that is S by r square. That is called the solid angle. So, you can actually define solid angles of surfaces subtended at some point. So, if I want to define the solid angle subtended by the sun on the earth, what I do is I calculate what is the. So, in principle I have to imagine a sphere of radius equal to the distance from here to the sun drawn. The sun will intersect that sphere in a certain area, which is the area of the sun, and I will calculate what is the solid angle subtended by the sun on my eye here. That will give me the solid angle of the sun. Similarly, I can calculate the solid angle subtended by the moon. So, for example, the solid angle subtended by the sun on earth is approximately 6.8 into 10 to the minus 5, and there is a unit called steradians. It is a unit of solid angle. Radian is the angle for is a unit of angle. Steradian is a unit of solid angle. So, the sun subtends a solid angle of 6.8 10 to the minus 5. The solid angle by subtended by moon on earth is approximately 6.7 into 10 to the minus 5. Almost equal. The sun is much bigger than the moon, but it is also much farther away. So, for the sun the area is much bigger. In this figure, if I see, the area of the sun is much bigger, but r is also much bigger. So, S by r square is the solid angle subtended by the sun on the earth. So, this is the point on the earth. I am sitting on the earth here and I am looking at the sun. The sun subtends a solid angle of S by r square. The moon is somewhere here, much closer. Its area is much smaller, but it is much closer to me, and it subtends the same solid angle. Now, actually the two solid angles are almost equal, and that is the reason why you can form complete solar eclipse. So, the moon can completely block the sun, because if you look in the direction, the solid angles subtended by the sun and the moon are exactly the same towards you, almost the same. So, the moon can completely cover the sun. Now, I leave a small problem to you. So, what is the So, I want to hold a sheet of paper, a small circular sheet of paper at a distance of 25 centimeters from my eyes. What is the radius of the circular piece of paper required to just block the moon? That means, I am looking at the moon. So, I must have a small, so my eyes are here. So, I must hold a small piece of paper here, so that the moon is covered. So, the moon gets completely covered by this small sheet of paper. So, I leave this problem to you, just try to estimate, and at night if you have some time, just go out and look at the small piece of paper and look at the moon, and you will see that you can actually completely block the moon by a small sheet of paper. So, this is the solid angle. So, you define the solid angle as the ratio of the area intercepted by this cone on a sphere of radius r divided by the square of the distance of that from the point of observation here, and that defines the solid angle. Now, just like as we discussed for the sun and the moon, if you take two spheres, say for example, one sphere of this size, another sphere which is bigger in size around this point, and if you draw a cone, so here they will intersect at a certain area, here they will intersect in a different area. So, let me assume this is R1, this is R2. Let me call this S1, this is S2, the areas. Because both of them subtend the same solid angle d omega, the solid angle here. So, let me call this solid angle as d omega. Please remember, this is small omega, this is capital omega, is equal to S1 by R1 square, which is also equal to S2 by R2 square. Areas S1 and S2 are different. This could be the moon, this could be the sun. Areas are different, distances are different, but both of them subtend the same solid angle. Now, let me imagine that I have a point charge located at this point. We have already seen earlier electric field lines. So, if it is a positive charge, these field lines are coming out radially away from the point charge. So, let me draw more lines here. Positive charge, electric field lines are coming out. So, I draw a sphere around this, and I draw another sphere. Notice two things. The number of lines crossing this inner sphere is the same as the number of lines crossing the outer sphere. These lines do not represent anything flowing. Please remember, these lines represent electric field lines. They are only directions showing directions of electric field. If the lines are closer together, like towards the center, the electric field is larger. If you move further away, the electric field lines get separated out and the electric field decreases. The number of lines crossing the inner sphere and outer sphere are the same. So, now let me take the lines which are appearing between two areas here. So, let me assume as before, the inner circle of radius r1 and outer circle of radius r2. So, how many lines? So, the number of lines crossing this area and the number of lines crossing this area are the same, because these lines do not intersect, and all those lines which are starting from here, if I draw more lines here, there are a certain number of lines crossing the area here, they will all be crossing the same this area also, because both of them subtend the same solid angle here. So, the area is increasing. So, the area of this area is increasing because d omega the solid angle here is S1 by R1 square is equal to S2 by R2 square. So, the area is increasing as 1 by, so area S1 is equal to R1 square into the solid angle d omega, S2 is equal to R2 square times the same d omega. So, as you can see here, the area covered by this the same solid angle on the inner sphere and outer sphere are different, and it is in the ratio of the radii. So, S1 to S2 is essentially R1 square by R2 square, and I also know that the same number of lines are crossing this area S1 and the area S2. and as I mentioned, the spacing between the lines represents something like the electric field. So, what happens is, because the number of lines crossing is the same and the area is increasing as square of the distance, the electric field must be dropping as 1 by square of the distance, which is nothing but from the Coulomb's law. So, electric field here and here has a ratio depending on the distance square area. So, area increases as square of distance, electric field decreases as square of the distance, with the result that the number of lines crossing here and number of lines crossing here are exactly the same. So, in the next lecture I will introduce the concept of flux, electrostatic flux, and we will then discuss the very important law in electrostatics called Gauss's law. Which will relate electric field to the charge, and it will be very useful. It is a very useful technique to calculate electric fields for given charge distributions or calculate the charge distribution for a given electric field. So, we will do this in the next class. Thank you very much.